Hello everyone, welcome to today's data visualization class. In today's tutorial, we will learn how to visualize Levy flight using Python. Okay, first of all, I want to introduce what is a Levy flight. Levy flight is a stochastic process, and it measures a trajectory including short jumps and occasional extreme long jumps. So let's take a look at an example. If we measure an item's trajectory, let's say this item starts at this area, and in this area, this item conduct very short jumps for multiple times, and at a certain time, at a random time, it will jump to another area, this area, using a long jump. And when this item arrives this area, it will wandering around using short jumps. And then at a certain time or random time point, it will jump to another area using a long jump and then wandering around and then repeating this process multiple times. And at the end of the process, it forms the Levy flight. So basically, the Levy flight composed with multiple short jumps and occasionally long jumps. And if you model the distribution of these short and long jumps, you will find that these two types of the jumps will follow the long tail distribution. So that means most of the time the item will using the short jumps, and for a small probability it will use the long jumps to reach a new area. So why Levy flight is very important? Because Levy flight, according to some scientists, a lot of animals using that Levy flight to search food. For example, some studies prove that sharks apply Levy flight to search food. Let's say this is a shark, and the shark will search food for this area. If there is no food, it will conduct a really long jump to a new territory and then start to search food. If there is no food, it will go another long jump and to a new territory. So in this way, a shark can using Levy flight to increase the success rate to find the food, and also it can reduce the energy because these two aspects can help the shark to survive in the nature. Okay, so we learned that what is the Levy flight and why Levy flight is important. And now let's go to Colab, and we're gonna try to model and visualize the Levy flight. So first of all, we need three libraries: NumPy, Matplotlib, and Seaborn. Okay, so first of all, we know that the jumps, or the steps, follows the long tail distribution, right? So this is a key element to visualize or to model the Levy flight. So we're gonna generate some steps, and these steps are composing some short steps and long steps, and they should follow the power law distribution. Okay, so how do we model these steps? So let's using this function. Let's say we're gonna model the long tail steps. Okay, and this is a variable, and this variable holds some random steps, and each element of these random steps comes from the power law distribution. So in order to model the power law distribution, we can using NumPy random dot Pareto distribution. So this Pareto function will help you to model the power law distribution. So we're gonna using parameter, let's say parameter a equal to 2, and we're gonna generate 100 steps, and then we're gonna visualize that. So we're gonna use Seaborn's histplot to visualize these long tail steps to see whether it is a long tail steps. Okay, so if we measure this, if we model these steps and visualize that, actually you can use KDE equal to true so that you can have this KDE line. Okay, so basically this distribution, this histogram, is actually the long tail distribution. You can see that there's a lot of frequency accumulated in those short steps, and for these long steps it occurs really small frequency. Okay, so this is how we model the power law for generating those steps. That is our key point. Okay, within this key point we can start to visualize the two-dimensional Levy flight. Okay, let's do this. First of all, we're gonna define the number of steps. And let's use n to hold that number, and we're gonna use 300 steps. Okay, and later on you can adjust the n size to model the Levy flight. Okay, the step 2 is we're gonna generate steps. Because we're gonna visualize the Levy flight through the two-dimensional coordinate system, so we have x steps and y steps. The x steps is the steps recorded on the x-axis, and we also have the y-axis because these two dimensions decide a point in the two-dimensional coordinate system, and later on we're going to use this point to compose the whole trajectory. So we're going to define x steps, and the x steps equal to, again, we're going to go back to this NumPy random Pareto function. Okay, and in here we're going to use a equal to 2, and you can adjust this value later on, but this is just for an example. And then we're going to use size equal to n, because this is our number of steps. So that is for those steps for one dimension. We need another dimension, y steps. Okay, so y steps equal to, again, we can just copy this line and paste in here, because we want to make sure that each dimension of steps are consistent to each other. Okay, so this is how we generate steps, and then we also we want to generate the angle, because think about, we model the shark's trajectory for searching the food, right? Because sharks, if you measure the steps has long steps and short steps, and shark can also adjust the angle for any random angle, right? So in order to do so, we're going to generate angles, and it equal to 2 times numpy.pi. So this is 2 pi. Represent, we're going to generate any number that within a circle. And then we're going to times numpy rand n. So basically, we also need to generate n steps angle, because every step you have a jump and a random angle. Okay, so that is how shark do the searching in the ocean. Okay, and then we're gonna we're gonna combine the step and angle together. So we're gonna define the steps and angle for each dimension. Okay, so let's say for the dimension x, and that equal to x steps. This is only the steps, but we also need to use the angle. For the angle, we're going to use numpy, cosine, and angles. Okay, so basically we generate a random angle and we apply cosine to give a little angle for all of these for this x-axis. And similarly for y, we're going to do the same, but this time we use the y steps, and we're going to times numpy sine function. You can switch that, but as long as it's kind of different, and that would be fine. Okay, so that is how we combine the steps and the angle for different dimension. And then remember in the last video how we visualize the random walk. We're gonna combine all of these steps to the trajectory, because the whole trajectory is what we're gonna visualize, right? And for these steps, we only generate single or individual steps. So here we're gonna turn steps to trajectory. Okay, so we learned in the previous tutorial, if we want to form the trajectory, we're gonna use the numpy sum function. Okay, so so this x represents the whole trajectory for the x-axis, and that equal to numpy sum, and we can just put the dimension x in here, and for the y, we're going to use numpy sum function, and we're going to pass dy in here. So in this way, we're going to turn all of these individual steps we defined in the previous session to the whole trajectory. And now our visualization is based on this whole trajectory. Okay, so let's run this cell. Okay, next, based on the trajectory, we're going to visualize the Levy flight. Okay, so when you visualize that, is quite simple. We can use plot function, and we can simply pass x trajectory and y trajectory for each dimension, and then for every point or every step, we can put them a little dot. So in this case, we're going to define marker equal to that represent a dot. You can use a star as well, but just a simple dot would be fine. And then you can define the marker size equal to 4. So that's it. And then we're gonna use plot.grade set up to 2. So the background has certain grade. And then plot.show. So let's run this. Okay, so this is our visualization for the Levy flight. You can see that most of the cases, this item is wandering for within a certain small area, and then it has some occasionally long jump, right? You can see that those long jumps are quite small compared with those short jumps, because these two types of the jumps follows the power law distribution. And you can run this again, because each time Python will give you different kind of steps, and each time the trajectory will be different. So your Levy flight visualization will be different as well. Okay, so this time it generates this way, and we do the third time, you will have this way. Okay, so this is how we measure, this is how we model the Levy flight using Python. It's quite simple, right? And hopefully you enjoyed this video, and I will see you next one.